Hello, we're going to look at some inverse trig functions used for integration. The top three formulas are the general formulas for sine inverse, tangent inverse, and secant inverse respectively. Basically, we're going to take a problem that's given, try to make it look as closely as we can to the left side of these formulas, and then once we do and identify a and u, then we can translate out and get our antiderivative. So let's just jump into some examples to check out how this works. This integral is 1 over square root of 4 minus x squared dx. I notice a square root and then a constant followed by a variable squared. That matches up with formula number 1 up here. Since 4 is 2 squared, I know that a is going to be 2. X squared lines up with u squared, so u is equal to x. The derivative of u is just going to be 1 dx. I put that in parentheses so you could refer to it. Okay, so matching up, a squared is 4, so that means a is 2. U squared was x squared. That means u is x. And so using this expansion or antiderivative formula from number 1, we have arcsine of x over 2 plus our constant of integration c. Second example, we have 1 over 2 plus 9x squared dx. That closely aligns with formula number 2. This is in the position of a squared, so if we have a squared equal to 2, that means a is equal to square root of 2. 9x squared is in the position of u squared, so 9x squared, if you were to take the square root, you get 3x. Note that the derivative of u is 3 dx. That will come into play in a little bit. Okay, so what we're going to do is we're going to rewrite 2 as square root of 2 squared. 9x squared is 3x squared. Now here's where that derivative line comes in. du is equal to 3 dx. Well, I didn't have a 3 in the original problem, so if I put a 3 in the numerator, I can balance it out with a 3 in the denominator. And that's from techniques we've looked at in the past. Everything is matching up. We have du, a squared, u squared. That's 3 dx, square root of 2 squared, 3x squared. And now using formula 2 in the expansion, 1 over a is 1 over square root of 2. This 1/3, that's where this 3 is coming from. 1/3 times 1 over square root of 2. Arctangent or tangent inverse, you can put either notation. U over a is 3x over square root of 2 plus your constant of integration. Okay, so when I switch to the next slide, we're going to do an example using this third formula. So if you want to pause and write this one down, feel free to do that. Okay, so we've got an example that's going to use secant inverse. We have the integral of 1 over x times the square root of 4x squared minus 9 dx. Let's note that u squared is 4x squared, so that tells us u is 2x. The derivative of u is 2 dx, and I made that little note here. A squared is 9, so that means a is 3. Now to get it in the right format, u, we have, let me line this up. Okay, so u squared minus a squared. That's under the radical. du is equal to 2dx. And then by putting a 2 here, because remember in the formula, before the radical gets there, we need u to be here. Well, u is 2x, and we only have 1x. So if I force this to be a 2x, then I've got to put a 2 up here to balance it out. Now we're ready to actually compute the integral, take the antiderivative. So that's 1 over a, arcsecant or secant inverse, you can use either one, of the absolute value of u over a, so that's the absolute value of 2x over 3 plus c. Sometimes the integration using inverse trig functions, they're disguised really well, and sometimes they're hard to recognize. We're going to do a couple of examples where that's the case. This problem, we have 1 over square root of e to the 2x minus 1. This one kind of fits the case of u squared minus a squared. And if you recall from the first slide, u squared minus a squared under a radical is closely fits to arcsecant or secant inverse. If it were reversed, where it's 1 minus e to the 2x, we'd jump right into arcsine. A is your constant, so it's out of order to use arcsine. But that's okay. Here we go. E to the 2x, that can be written as e to the x squared. 1, that's still 1 squared. So that helps us identify u and a. U is e to the x, a is 1. U and a. Okay, now the derivative of u is going to be e to the x dx. Solving for dx, we divide by e to the x, which was our original substitution. So dx can be replaced with du over u, and that's what I did here, divided by the square root of u squared minus a squared. Dropping the u to the denominator, we have du over u square root of u squared minus 1. And that actually makes a really good lineup from Formula 3 on the first page. We have 1 over a, which is 1 over 1, times the arcsecant of absolute value of u, which is e to the x. Now, since e to the x is always positive, you can remove the absolute value. Dividing by 1 keeps it the same, plus c, and that gives us our antiderivative, or the indefinite integral expansion. And then finally, for our third example, this is one that's also disguised, and it's a really good reminder of completing the square. If I can get this to look like something squared plus something squared, then that fits tangent inverse perfectly. Refer back to the first slide, Formula 2. Okay, so let's remember how to complete the square. I'm going to take this denominator, and then I'm just roughly going to set it equal to y long enough to get the completing the square done. Okay, so if I want to write the denominator as the sum of two squares, then what I do is I'm going to leave the x's together, move the 7 over, it'll become negative 7. Completing the square, remember you take half of the coefficient of x, which is negative 2, and you square it, and that's positive 4. The square is what you add to both sides. This right side factors as x minus 2 times x minus 2, which can be written as x minus 2 quantity squared. Negative 7 plus 4 is negative 3. Re-isolating y, you add 3, and now we've got our squares. This can be written as x minus 2 quantity squared plus 3. which can further be written as x minus 2 quantity squared plus square root of 3 squared. That's going to be just 3. But we write it so that we can recognize u and a. U is x minus 2. Its derivative is just 1 dx. And a is square root of 3. Using formula 2 from the first slide, we have 1 over a. That's 1 over square root of 3 times tangent inverse of u over a, which is x minus 2 over square root of 3, plus our constant of integration. I hope this video has helped. I tried to keep it brief. Check your Google Drive folder if you want to review the slides without my voice. You can also check out Google Drive and find extra homework help. I try to go through and work all the homework problems that you're assigned. Mine will be just differing by a little bit, but I try to do that so you can have extra examples to look at. Some of these problems are very straightforward, some of them are not. But if you have any questions or concerns, reach out by email or phone, come by the office, or just ask in class either way, and I'll try my best to help you out.